Hello, and welcome to the next video in my series on finite mathematics. Now, a few things before we get started. Number one, if you're watching this video because you're having problems in a course, I want you to stay positive and keep your chin up. If you're watching this, it means you've come pretty far in your schooling up to this point, and this may just be a temporary rough patch. So with the right amount of hard work, practice, and perseverance, you can get through it. I have faith in you, and so should you. Number two, please feel free to follow me here on YouTube and or on Twitter. That way when I upload a new video, you will know about it. And on the topic of the videos, please leave a thumbs up if you'd like it. Or if you think there are some things I could do better, please leave constructive comments below, and I will definitely try to incorporate that into future videos. And finally, just keep in mind that these videos are geared towards individuals who are relatively new to finite mathematics. So the examples I will be going over are very basic, and I will be explaining them in great detail, step by step. So not only do you know what's going on, but why. So all that being said, let's go ahead and get started. So this video is the next in our series on Markov chains. So we've done all kinds of videos up to now, from the very basic of what a Markov chain is, up through a few transitions in them, to many transitions, and now we're coming to sort of the end point, at least in my work with Markov chains, and that has to do with steady state vectors or steady state matrices. So there'll be at least this video and maybe one or two more on Markov chains. So this is just a continuation of what we've been doing. Now I will assume a few things. I will assume in this video that you know the basics of Markov chains, what they are at their most simple level. I will also assume you know how to do simple matrix operations like adding and subtracting matrices, multiplying simple matrices and things like that. Otherwise this isn't going to make any sense. So hopefully you've watched my other videos, or you've gotten enough out of your classwork, textbook, or notes to understand the basics of Markov chains and simple matrix operations. Okay, so let's go ahead and get started. Now this is just a continuation of the previous video, so I'm not going to go back and explain the entire example as far as the wording of the word problem goes. So if you want to go back and look at that, feel free. But really for this video, you don't need to know a whole lot about that. This is more about the mechanics of doing some long-run Markov chains. So in the previous video, we talked about this general structure for long-run Markov chains. On the left-hand side, we have an initial state vector, and that is our probabilities right now. How the probabilities are distributed, maybe in the general population or through our customers or whatever else that might be. Then we have the transition matrix, which defines the probabilities by which individuals or whatever can transition between different states in our Markov chain. So in our example, we have drivers that were either high risk or low risk. And then when they renew their insurance policy, we look at their driving record for the past 12 months, and then based on that, they are either put in high risk or low risk. And then a year goes by, we do the same thing. Then they are put high risk or low risk. Another year goes by, etc. So once they are inside the insurance company, the transition matrix is the probabilities by which our customers move between states when their policy renews. And then finally, on the equal side of this equation, if we take this many steps in the future, and you'll notice there the transition matrix has an exponent, m, and that just represents the number of steps from now we are interested in. So if we had a customer that comes in the door, and that customer is with us for 10 years, and we want to know the probability that that customer is either high risk or low risk, we would put 10 where m is. So that's just a basic review of the matrix operations in Markov chains. So we write it like this. So after a certain number of steps, we can figure out probabilities of being in any given state. So V is our initial state vector, P is our transition matrix, and M is the number of steps into the future we're interested in. So you can see there at the top, V times P times P times P, etc., etc., etc. Well, the number of times we multiply P by itself is the number of steps into the future we're interested in. So again, anything times itself, if you do it multiple times, you can just write that as an exponent. So that's all that means. Now, when we did that in the previous example, we came up with this. So all we did in these examples here is we changed the exponent. We changed the number of years into the future we are interested in. When we got down to 20 years into the future, we did 20 years, which is there at the bottom left, and then we did 25 years there at the top right, and something kind of strange happened. The probabilities seemed to have stabilized. They steadied out. And no matter how many more years into the future we went, they didn't change. They stopped changing. So we call that a steady state vector. Now we'll say here, steady state vector and steady state matrix, sometimes those are used interchangeably in finite math courses, and that's fine. So here was our 25-year distribution vector or matrix. Now, how do we interpret this? Well, it would appear that after 25 years, approximately 27.3% of our drivers will be moving to high risk. On the other hand, 72.3% will be moving to low risk, regardless of what they were in the year before. And that's the important thing. It doesn't matter what category they're in. Right now, after 25 years, when it changes, the probabilities stay the same. And this is kind of a basic risk profile for the insurance company. And again, it's very basic. Insurance company models are very complex on demographic data and stuff, but this is just a simple version. The important thing to get here is that once we get past 25 years into the future, the probabilities cease to change. So if we continue to multiply our answer by the transition matrix again and again and again and again, it has no effect on the outcome. So 25 years into the future, the probabilities are the same as 50 years into the future. So we can write this in a general form as V times P equals V. So again, V is our initial state vector, P is our transition matrix, and when we multiply those together, we get our initial state vector again. So the P there kind of acts as the number 1, right? Because anything times 1, you get that back. So P is kind of like the number 1 there. So multiplying by P, the transition matrix has no effect. It just returns V again. So drivers will continue to move between high risk and low risk in this example, many years into the future, but the numbers that go in one and into another will become the same. So the proportions will stay the same. Okay, so in real world terms, that's kind of what it means. But if you look at this general form here, this just begin to make sense. No matter what we multiply our transition matrix with, we end up getting the original back. So here's some general form. Okay, and we're going to do some simple algebra here. So remember, V is our initial state matrix, P is our transition matrix, and when we multiply those together, we get V back. So our initial state vector, which in most places we won't know. So in this example, it's just X and Y. We're not sure what they are, and that's how these problems are actually set up. We're trying to find the steady state vector or the steady state matrix. So that's an unknown. So V is unknown. Our transition matrix there in the middle is known. And on the right hand side, we're going to get V back. So you can tell here we're going to be solving this problem for X and Y. So in this case, our unknown steady state vector is V. And we also know that V is X and Y, and that's what we're solving for. So let's do some operations here. We're going to multiply the matrices on the left side together. So the matrix XY, we're we're going to multiply that by our transition matrix next to it. Now again, I'm assuming you know some basics about matrix multiplication, but I'll try to walk you through it the best I can if you need a little brush up. So what we're going to do is we're going to multiply the row xy with each column in our transition matrix. So when we do that, we get this. So x times 0.6 is 0.6 plus y times 0.15 is 0.15y. And you can see there, if we kind of take the xy matrix and flip it on its side, and then we multiply x times 0.6 and y times 0.15, that gives us the left-hand side of our answer down here. Likewise, we have to do it with the next column. So x times 0.4 is 0.4x plus y times 0.85 is 0.85y. So simple matrix multiplication. And of course, that equals xy still. As you can see, the way we've set this up is that the expression 0.6x plus 0.15y has to equal whatever x is on the right. So you can see the red arrow indicating that those have to be equivalent. Same thing with the right expression. 0.4x plus 0.85y has to be equivalent to whatever y is. So again, we're solving for x and y, and this is just sort of an intermediary step to doing that. Now we're going to set up a system of equations to go ahead and solve this. So we know that the left expression is equivalent to x, and the right expression there in the blue is equivalent to y. So we can set this up as a system of equations. So 0.6x plus 0.15y equals x, and that's just the red arrow there at the top. Likewise, 0.4x plus 0.85y has to equal y. That's the blue arrow at the top. So now we have two equations that we can work with. So there are those equations again. Now we have to do some steps. First thing we're going to do is we're going to subtract x and y, top and bottom respectively, to set each one to 0. So on the top, we're going to subtract x from both sides. On the bottom equation, we're going to subtract y from both sides to set them equal to 0. So we do that, and that means on the top we have 0.6x plus 0.15y minus x equals 0, because we subtracted the x from that side. Down at the bottom we have 0.4x plus 0.85y minus y equals 0. And that's just basic algebra. We subtracted x from both sides on the top and y from both sides on the bottom. Now we just combine our terms and simplify each equation. So when we do that, on the top we end up with negative 0.4x plus 0.15y equals 0. And on the bottom we have 0.4x minus 0.15y equals 0. And again, that's just combining the x and y like terms in each equation. Now that should look pretty peculiar because they look almost identical. And if we multiply the top row by negative 1, changing the sign of each term, they are the same. So remember, we can multiply an entire equation by a constant, and that's fine, as long as we do it to the whole thing. So these equations are actually the same. They're actually equivalent. Now, since these equations are the same, we can actually collapse them into one equation. So now let's do some cleaning up. So again, those two equations are the same. Since they are the same, we can collapse them into one because it's just redundant. You know, in linear terms, it's the same line on a graph, but they're the same, so we can just collapse them into one. So there it is. Now, what else do we know about this problem that has to be true? Well, we know that our initial state vector has to equal 1. It has to add up to 1. So whatever x is and whatever y is, they have to add up to 1. And that's a very important component to these type of problems. So now we have two equations we can use. And these are the final equations we will use to find our steady state probabilities. So let's solve this system of equations. And again, this is back in, probably 8th, 9th grade or whenever you had this in algebra. So this is not too difficult, but I'll walk you through it. So there are two equations. So our first step, we're going to multiply the top equation by 0.15. So we go ahead and do that. And as you can see, everything is just 0.15x plus 0.15y plus 0.15. Now what we can do is we can add down. We can add those equations. And in the process, we will eliminate y. I forgot a y right there, my apologies. But we can eliminate y. So we go ahead and add those equations together, and we end up with 0.55x plus 0, or 0y, equals 0.15. So we multiplied the top by 0.15 because by then adding them together, it would allow us to eliminate one variable, in this case y, so we could solve for the other, x. So we solve for x and then y. So we know that 0.55x equals 0.15. So we got to do some simple division, divide 0.55 from both sides. So x equals 0.15 divided by 0.55, and that is x equals 3 over 11, or 3/11ths. And that is our solution for x in our steady state matrix. Now, we got to solve for y. We know that x plus y equals 1, and we just found the value for x, so we go ahead and substitute that back in and then solve for y. So 3/11ths plus y equals 1. We'll subtract 3/11ths from both sides. Y equals 8 over 11. And if you notice, 3/11ths plus 8/11ths is 11 over 11, which is 1. So, that's our solution. This was our original problem. We had some unknown initial state vector that when multiplied by the transition matrix gave us back our initial state vector. And those values turned out to be 3 over 11 and 8 over 11. So you can actually do this in your calculator if you want to. If we take our answer, 3/11ths and 8/11ths, and then multiply that by our transition matrix, we will get back 3/11ths and 8/11ths. And that is sort of the idea or the definition of a steady state vector. Remember that when we multiply v times p, we get v back. So remember when we did this by numbers, this was our initial state. We had some numbers, and 0.19, or 0.1 and 0.9, and then we took our transition matrix 25 years into the future, and we ended up with 0.27272 and 0.72727. And guess what? Those values are 3/11ths and 8/11ths. So our initial state, or steady state, our steady state vector is 3/11ths and 8/11ths, which is the exact same thing when we sort of roughed it by taking the transition matrix many years into the future. Okay, so that is our at least first video on steady state vectors. And remember, it's just sort of the other way of figuring out what our transition matrix will even out to in the long run. Now, not all transition matrices will, but in this case, of course, that happened. So we're going to do a couple more videos probably on this, doing more examples that get more complex as we go. But again, it's just a way to figure out the exact steady state matrix using algebra and some simple matrix operations and things of that nature. Okay, so just a few reminders before we sign off. Number one, again, if you're watching this video because you're having problems in your class, I want you to stay positive and keep your head up. You are smart and talented. I know you can get through it. I have faith in you, and so should you. Please follow me here on YouTube and or on Twitter, so when I upload a video, you know about it. If you like this video, give it a thumbs up, add it to a playlist, or what have you. Or if you think I can do better, please leave a constructive comment in the comment section below, and I will try to take that into account as I make more videos. And finally, most importantly, I want to thank you, the viewer, for watching. I wish you the best of luck in your studies, and I look forward to seeing you again next time.